All right. So I think I remember I asked, oh, that's pretty loud. I think I asked before how many people have been exposed to discrete choice models. And I think there were maybe 5 people that had, so I just want to ask again, how many have used discrete choice models? So maybe, yeah, maybe about 7 or 8. Okay. My personal view, and I think a lot of people would share this view, that that discrete choice models are some of the most interesting models that we use in transport, and they're interesting because, unlike a lot of the other models that are just mainly set up to support certain data types and a whole variety of research questions, there's a philosophy that underpins the discrete choice models in transport sector. There's a whole behavioral set of principles that underlie the models. They don't have to, but and that is, I mean, you can use the models without those behavioral principles. But when you do add the behavioral principles, the models become really, really quite amazing. So, so we're going to spend some time. Because of that, they're a bit more complicated. They're not only complicated in the form of how they're estimated and how we use them and how we interpret them, but they're complicated in that they're tied to the behavioral theories. So that's why this lecture about these models takes a little while. So we'll actually have two lectures to build up to get enough information to start to do these. And these models are really, really interesting to use and to estimate. And so you'll be very happy to learn these models. Okay. Boy, this seems to keep happening. Okay, so oh, no, sorry about that. Okay, so discrete outcome models. So these models are the case when we have nominal scale variable as the outcome. All right, so we've started with linear regression where we have a ratio variable as the outcome. And we went to count models where it's a special case, kind of a special case of a ratio variable, positive valued integers. And now we have the case where the outcome is a nominal scale category, not an ordinal, nominal. And so that's interesting. So if you think about what we've done so far, and you think about the linear regression model, we can't just develop a model framework that would have just y as a function of beta x, because y has no order, right? When I show the plots of y versus x, I always have y as one variable and x is another, and you have scale for both. But nominal variable doesn't have a scale like that. So we have to completely rethink how we do these models. And so the discrete data are modes of travel. So automobile, bus, rail, walking, cycling, carpooling, you name it, however you want to put it. Class of vehicle owned, sport utility vehicle, van, compact vehicle, subcompact vehicle, et cetera, et cetera. Type of accident. So you could say that type of accident actually is an ordinal variable because you could apply some scale to that. But you could also, so if I had something like type of accident, oh, sorry, those don't have order. If I had severity of accident, I could treat as a nominal, has order, but type of accident doesn't, just run off road, rear end. But if I did have a ordinal, and I was thinking about the severity of accident, and I treated it as nominal, what would I be doing? to the scale of the variable. Remember the discussion we had earlier? So I've gone down on the scale. I can take the ordinal and I can discard the information about order and use the nominal scale variable. So you can always often go that way, but you can't go up. And so that would be a criticism of doing that. One criticism of using a discrete choice model to model accident severity, because you're discarding the information about order. And then there's the other examples, right? So they're not order, and there are, as you would guess, different models to model ordered data or ordinal data, and they're similar to these models, but in some ways more limited and not as interesting in my view. Okay, so we start from a very basic principle that the models of discrete data, we're going to start with some concepts and we're going to dive into the form of these. So we start with a linear function of covariates that influences specific discrete outcomes. So we're not going to talk about any theory yet. We're going to come back to that of behavior or anything like that. So all we're going to say is let t sub in be a linear function that determines discrete outcome I for observation n. Okay? Such that it's some linear function of beta x. We've all seen beta x before. So we're notionally, conceptually saying that t for outcome I, so there might be 4 potential outcomes and an observation. So let's say there's 4 different modes of travel available for people, and we say that the probability of them, some individual choosing one mode bus is some linear function. And the parameters, just like in every model, we have parameters that we're going to estimate, and we think that there are some vectors x that would influence that, that model. To arrive at a statistically estimable model, we have to add a disturbance term, just like everything else, right? Where there's uncertainty in the process, these are stochastic models, so we say that we are going to have to account for the stochasticity in this process. So we add the error term epsilon sub in. Okay? So we add the disturbance term because there are emitted variables in the process, in that function. We could be not perfectly specified in the relationship. There could be proxies that are used. I haven't used that word yet. Proxy variable is a variable that is something that we think it's really kind of a measurement error, that a variable we use to capture some underlying process. And then variations in beta that are not accounted for. Okay? So those are the reasons we need to do that. So to derive an estimable model, we go through a little process, and I'll walk you through that process. So we say that all possible outcomes are in some larger set of outcomes, capital I. Okay? And that the probability that individual n is associated with outcome I, okay, is the probability of observing n having discrete outcome I, okay. I is a subset of all of the outcomes in large I, is what we see up here. So, and what we say is the probability that that outcome I is associated with observation n is equal to the probability that the t sub in is larger than or equal to the t sub in, where this I is not equal to I. So, in other words, we set up this notion that the probability of this is equal to the probability of the outcome being I is greater than the probability of all the other potential outcomes. So let me say it this way. I'm just looking to see, well, what's the probability of bus, auto, van, and train. And I'm just going to say, well, to look at the probability of bus, I'm going to make sure that it's larger, that this T sub n for the bus is larger than the T sub n for all the others. Okay? The rail, the train, etc. And then substituting TIN, we're going to put in the linear function. So the probability that outcome I is associated with individual n is equal to the probability of this linear function plus its error being greater than, for the outcome in question, I. So this is outcome I. So we say the probability, this probability is going to be greater than or equal to all of the other probabilities associated with all the potential other outcomes. Okay? So really, in a sense, what we're saying is the probability is equivalent to the highest probability outcome in the outcome set. It's still not a derivable model at that stage. This is still conceptually building the case for one. So so we have to go a little bit further to make this a reality. So from here, we have to make some manipulations to get these to work, these models to work. So estimable models are developed by assuming a distribution of the random disturbances epsilon. So there was a question asked earlier today in the tutorial about the Gumbel distribution, or maybe it was in lecture. And I said oftentimes we make assumptions about distributions for analytical convenience. So here's another example of when we're going to do that. So we have to specify, as you might guess, we're going to use maximum likelihood methods to estimate these models, and we have to specify what these error terms look like. We've rearranged the model slightly. So now what I just want to walk through this so we understand it. The probability that observation n, it could be an individual, it could be something else, but observation n is associated with outcome I, is equal to the probability that the deterministic part of observation I minus the deterministic part of all of the other options is greater than the error of all the others minus the error of the outcome of interest. It looks kind of like a strange specification. But so it's the difference in the structural linear functions being greater than the difference in the error terms. So that difference in error terms is what we're going to have to make an assumption about. And so to understand these models, really what you need to understand is that these models are all based on, different models fall out of what we assume that difference in error terms to be. Okay? So the first class comes out, binary and multinomial probit models arise when the disturbance term is assumed to be normally distributed. So that difference in normals, or normal difference in error terms, is assumed to be normal. So this equation estimates the probability of outcome 1 occurring for observation n, where epsilon 1n and epsilon 2n are normally distributed with mean equal to 0, variances sigma squared 1 and sigma squared 2, and covariance sigma 1, 2. So an attractive feature of normally distributed variates is that the addition or subtraction of two normal variates also produces a normally distributed variable. So interesting property. That's one of those properties that statisticians have determined. Have normal variables, and we add them or subtract them from each other. The result is normal. That's not always the case. But for normal, yes, for normal distributions. Not always the case for other distributions, but it holds for normal. So, and in this case, the E2n minus E1n is normally distributed with mean 0 and variance sigma 1 squared plus sigma 2 squared minus sigma 1, 2, the covariance. The resulting cumulative normal function is as we see here. Okay? Luckily, we don't have to do that kind of any manipulation with that. The software does all of this for us. And where we call this function the standardized cumulative normal distribution. Okay? And that's so that this function here is the standard cumulative of this. Okay? Where's all this going? Let me show you this curve, and if we understand this curve, we are in really good shape. Unfortunately, but I can. Okay, so for some reason in the full screen mode that this chart isn't showing well, but I'm going to show it here. So what I'm showing you, and if you get this curve, you'll get how these models work. Okay, so even if if everything we just went through in the equations doesn't make sense, let's make sure this makes sense. Okay. What we've got here is two potential outcomes, 1 and 2. Okay? So let's say a binary nominal variable. It's going to either condition 1 or condition 2. Say pass the test or fail the test, whatever. And so this is the curve that is produced by, or a hypothetical curve that's produced by the model. Now what happens here is that this x-axis is the difference in the structural component of these models. The x's associated with the first outcome and their betas, and the x's and their betas associated with the second outcome. Okay? And remember we've said that those linear functions are equal to the probability. So in other words, this is a function of the probability of the first outcome, and this is a function of the probability of the second outcome. Now, this is actually 0, this point. It doesn't show it on this x-axis, but this is 0 right here. The 0 point on the axis is when the probability of the first outcome is equal to the probability of the second outcome. So they're equal, so the subtraction is 0. And the model predicts when there's 0 that there's a equal chance of there being the first outcome as there is the second outcome. Okay? So that's how these models work. So in this case, in the simple case, the 2 outcome model, it looks at the difference in linear functions that are equal to the probability, and we're estimating x's that are associated with the probability of event 1 or outcome 1, and x's that are associated with the probability of outcome 2, and we scale it such that we get a curve, a model that predicts this curve. And so as you get closer and closer over here, what happens, so we're positive now. So positive means the probability of this one is much larger than that one, so x1. This curve is the probability that 1 is chosen. So probability up here is 1. So as we get over here, x1, beta 1, x1 starts to overwhelm, and the probability goes up and up and up. And as we get way out here, it starts to approach 1. So we're almost certain that the outcome 1 is the right out, or the outcome of that individual, because the probability of 1 dwarfs the probability of 2. And the same thing happens over here when we're getting negative below 0, that the probability of beta 2 times x2 is much larger than 1. We get quite negative, and the probability of the outcome being 1 starts to get very low. approaching 0. Okay? That's the probit model. So we have these functions so a linear model, we have a linear function that predicts an outcome, and we can plot that on a two-dimensional curve, right? Why? Y hat? Well, in this, we're predicting P. So one of the differences of these models versus both the count models, which predicts, remember the count model predicts a mean count. The linear model predicts a mean response. This is predicting, if you will, a mean probability. And that makes sense because we're dealing with nominal data. So we've converted a model that predict actual physical outcomes to models that predict probabilities of outcomes. And in this case, we have 2 outcomes. And I have a simple curve that shows the probability of 2 outcomes. Now, we're going to often have more than 2 outcomes. And so this curve goes into multidimensional spaces where the model simultaneously predicts the probability of more than 2 outcomes. What's critical here is that the probability is always summed to 1, right? So if we're over here, the probability of if it's 70, 80% of being the number 1, then it's going to be 20% of being number 2, or outcome 2. Same thing would hold true if we have 4 outcomes. The sums of all those probabilities by the model will have to sum to 1. Okay? So we could assign and have a model that would assign probabilities for the different outcomes for a set of x's. That's exactly what's happening here. Set of x's, and the model predicts the probability of it being the first outcome or the second outcome. Okay, does that make sense? Okay. Let me go back to the other view. So the parameter vector beta is readily estimable using standard maximum likelihood methods. So the probit model is a very good model. We can estimate it. It assumes normally distributed errors, and it's really easy. What we would then be modeling, in this case, a 2-outcome model, a binary variable, an indicator variable, right? 2 outcomes. So. And we've even some of the modeling so far, we've had a number of things that have had 2 outcomes. Those are not usually the most interesting ones. Usually the interesting ones are where there's a lot of outcomes. Okay, so what we would have then is the likelihood then becomes, it's actually pretty straightforward to conceptualize, the likelihood becomes the probability across all outcomes, across all individuals or samples, n, the probabilities of all those things. That's the likelihood, right? And then we use the log likelihood because that's simpler, and we end up getting, for this model, a log likelihood function that we solve. And remember, we're maximizing the log likelihood function. Sorry, I'm just trying to keep up on. I think she caught the flight. I'm just trying to get the flight details. And yeah. Yeah, she did, or she's getting on, but anyway. Okay, so the problem with the multinomial probit is that the outcome probabilities are not we can't solve this model very quickly with very large numbers of outcomes. It requires a numerical integration to solve for the betas, and it's a very difficult one. So statisticians have worked on this problem, and it actually requires, even today in very fast computers, a lot of computing time. So it used to be that if you had even tried, so 10 years ago, if you even tried a model with 3 outcomes, it would slow down considerably. So 2 outcomes is quite quick, but then you do 3 outcomes, and the numerical integration inside the computer and the techniques to numerically integrate became very, very difficult. So now we're at the point where we could do 5 or 6 outcome models fairly quickly, but it starts to get really, really slow, even today's computing power, when you go 7, 8 outcomes. And so it has generally not been used for that reason, because of the numerical difficulty in integrating and finding the parameter values. So what's happened is we've had mostly show up on the scene are this what we call the multinomial logit. So what we had before was the probit. And the probit is just a discrete choice model with a normally distributed error assumption. The multinomial probit is a slightly different formulation, and we did it, and it's been developed because it's analytically more convenient. So from a model estimation perspective, a desirable property of distribution of disturbances is that the maximums of randomly drawn values from the distribution have the same distribution as the values from which they were drawn. And the way this model works is that, and I'll show you how we come up with it, but it's going to be slightly adjusted so that what we do is compare the distribution, or this linear function, as being greater than the maximum of all the other outcomes. And we do that only simply because of analytical convenience. And the normal distribution does not possess the property, that same property. So therefore, the maximum of randomly drawn values from the normal distribution are not normally distributed. Okay? So the maximums of extreme value distributions are extreme value distributed. A disturbance term distribution with such a property, it simplifies this model enormously. So we can model 20 outcomes and analytically in a computer and do it fairly quickly with this analytical convenience. Distributions of the maximums of randomly drawn values from some underlying distribution are referred to as extreme value distributions. The extreme value distributions are really, really interesting distributions, and I still need to give you an abstract for tomorrow, but I'll talk tomorrow about extreme value distributions and how we're using them in some current research. There are 3 different types. We don't really need to know that, but there are 3 different types of extreme value distributions. Type 1, type 2, and type 3. The type 1 is referred to as a Gumbel distribution, typically. And I'm not going to belabor this. This is in the book. I just want to show you what, these are just parameters of the Gumbel distribution and the expression of the Gumbel distribution. Some strange mean, location. So oftentimes we'll talk about location, parameter, and scale. So this has 3 parameters. So some distributions have, so the most complicated distributions actually have 4 parameters. So there's a beta distribution that has 4 parameters. And this one has 3. And here's some examples of these extreme value distributions. All right, so what does it mean? So to derive an estimable model using a different distribution than the normal, one that's analytically convenient for us, we express this model in this form. And we say that the maximum of the, because of this maximum thing, we say the maximum of the beta ixi plus, so the maximum one, the maximum linear function of all the potential outcomes is extreme value distributed. Type 1, so Gumbel. When that's the case, we can, this entire model simplifies down. And so the disturbance terms, so we end up taking the difference in disturbance terms of Gumbel distributed variables, has a very nice property, and I'll let you go through this if you want to see the derivation of this. I want to get to the form and get you, and we can back up to this if you'd like. What we end up getting, so all we've done there is substituted a Gumbel distribution for two normals, taking advantage of the fact that we can draw maximums of a Gumbel distribution. Those are still Gumbel. And then do the math for the differencing of those error terms in the model, and we come out with a different form of the model. And all the choice models are formed that way, based on what distribution you assume. What we end up with, it looks the same, all right? But it's the probability that the outcome I is greater than or equal to any of the other outcomes. And we get a type 1 variance with commonly scaled parameter, which is logistic distributed. The final form, and it's actually all of this hassle we go through, comes up with a very simple, nice, clean form, surprisingly. So a lot of complicated math actually the math that, and a lot of other things associated with this model, the derivation of this model and a number of other things won a Nobel Prize. So, so this is really, really good economic or econometric stuff. So Daniel McFadden is the person that won the Nobel Prize for a lot of this work. And it was mainly on discrete choice models. And mainly in the transport sector, although he does discrete, it applied to a lot of other sectors as well. So what we end up with, I'm going to show you the final form. So here's the likelihood, the log likelihood of this model. The difference at the end of the day is very small, very minor. So this is the same curve we had, and again, I'm not sure why it's displaying, but what we see is the normal distributed is the solid line, and using all this fancy math, the models are very close to one another. We get a model that is a little more conservative and a little bit of an estimation, but has a similar property, so it would line up here. So the dash line is what we get from this other model. Okay, so it's still nicely behaved. It still captures the choice behavior. And it's very similar to what we started, but a heck of a lot easier to work with. Okay, and in our lab we can do both. We can do a probit model and we can do a logit model. Okay, so hang on one second. So this form here is the final form of this model. It's very, very simple, okay? And the way this expression is, so this is the predictive equation of the model. Okay, so the predictive equation of a linear regression was y hat is equal to beta naught plus beta 1 x1 plus beta 2 x2. That is what you use to predict. This is the final form of the the multinomial logit. And let's just go through this one. It's the probability that for observation n takes on outcome I, or is outcome I, is just a ratio of probabilities, or a ratio of functions. The numerator is the exponent raised to the linear function of the outcome I. Okay? The x is associated with outcome I, divided by the sum of all of the others. So it's the sum of this linear function for all of the other outcomes, including I. Okay? So if there are 3 outcomes, it's you're looking at the probability of it being the first outcome. This numerator would be the linear function of the first, and this would be the first plus the second plus the third. Okay? and the linear function, so the exponent of all three added together. It's a very simple function. You can program it in 3 minutes in Microsoft Excel. But luckily, the software can predict from it as well. So there's the likelihood, and we talked about that. Okay. Now, we're going to come back to that. And I've talked about it very generically. There's no mention of any philosophy or anything associated with it. You can actually use what I've talked about there to estimate models of outcomes. So, for example, you could model the probability of the crash type, the type of being a rear-end crash or a rollover crash, whatever. Okay, but if we want to start modeling the outcome of people in making choices, which is probably the most interesting and the most common application of these models. And people make choices in transport and civil engineering all the time. And their choices are very interesting to us. And what influences people's choices is very, very interesting to us. And if we talk about choices, then there's a whole theory around this. And this is also wrapped up into the Nobel Prize and everything that Dan McFadden did as well in the development of this theory. So, we introduce a notion of utility maximization. Has anyone have heard of that before? Utility maximization? Okay, so most of you have, not everybody has. Okay, the notion is that, and it's simple and it's really beautiful and wonderful to use. But the idea is pretty straightforward. When we make choices, we maximize the utility of the choice. And the argument would say it doesn't matter how simple the choice or how complex the choice, we maximize the utility. So when we are confronted, and I open my drawer in the morning and I look at the different socks I could choose to wear in the day, I will choose the socks that maximize the utility. The utility might be that I think, and I say I think because my fashion sense is not that great, but I think that it might go with my pants or my shirt, and so I might pick the socks. That might be as simple as it is on the utility maximization of my sock choice. But in the utility maximization of the vehicle that I decide to purchase, or the mode I decide to take to get to work or to school, might be a much more serious choice that would have a lot of factors that could influence that. And so as researchers, the interesting part is, what do we need to know about the choice behavior and factors that affect choice so that we can understand what we call the utility functions associated with choices. And there's a few really peculiar, interesting parts and features of this model. Okay, if you remember back in the model, I'm going to go back to the equation to cement this idea. There is, all we observe is the ratio of factors that influence. So what we're going to do is estimate utility functions. Utility functions are going to be a function that says what the x times the beta are proportional to the utility, how much usefulness someone gets from a choice. So if you think of these in terms of utility functions, this equation only has relative utility, the utility of this outcome I divided by the utility of all of the others. So a unique feature of these models is that, and it's something a lot of people have trouble getting used to, is that we only talk in terms of relative utility or relative choice. And it's different than our linear regressions and our other models most other statistical models. We don't have relative things. And I'll show you, it shows up in modeling it. It creates a number of difficulties for us. Let's talk a little bit about the derivation of the economics underlying this. so we talk about decision makers maximizing utility based on prices of alternatives and income constraints. So the idea that we make choices, a lot of times these choices have cost implications. We have cost constraints. We don't have unlimited supply of income. And so often costs are involved in some of these choices. We can't isolate specific choice situations. So in other words, if I wanted to look at purchasing a car, it's difficult to isolate that choice context because the car is just one of many things I might have to spend money on. I also have to spend money on my housing and my clothing and my food and everything else. And so to isolate that choice context is quite difficult. So we have to put restrictions on the utility functions in order to isolate specific choices. And so we do that by specifying our utility functions as this here in the bottom, that a utility function is a function of these consumption of M goods. Okay? And this is referred to as an additive utility function in nearly all applications is unreasonably restricted. So Dan McFadden and others had to get around this, but the application of this assumption implies that the acquisition of two types of breakfast cereals are independent, although it's clear that the purchase of one will affect the purchase of the other. A more realistic restriction on the utility function is to separate decisions into groups, okay, and assume that the consumption of goods within the groups is independent of those in other groups. So that's how we typically apply these models. We talk about choices within the context of similar choices. So we wouldn't, for example, look at choices of cereals and clothing or food and clothing and vehicles all in the same choice context because it wouldn't make sense. It's too hard you can't isolate those kind of things. But we could talk about just vehicles or mode choice or a set of alternatives within a specific choice context. So we call it separability, and we rely on separability in the economic literature to be able to set up and design the experiments that we're doing in these choice models. Okay, so actually what we have are indirect utility functions. So we're going to estimate indirect utility functions and maximize subject to the income constraint. And this maximization produces a demand for goods. When applied to discrete outcome models, the utility function is typically written with prices and incomes as arguments. Okay, that is, they're x's. And so we're going to often, when we look at choice, we will think of everything that would in fact affect someone's utility. Would price be a positive utility or a negative utility? Increasing price? Yeah, right? So things cost more, it means it becomes less attractive, right? That's a very easy concept to grasp. And you can, when you think about utility functions, you can often think about all the attributes and very quickly come up with whether things should be positive or negative on the utility of something. So the relationship between the indirect utility and the resulting demand function for a good is given by Roy's identity. And all of this is underlying the models that we see and we use in transport. The V is the indirect utility, the price of a good, the decision maker's income, and the utility maximizing demand for the good. So when we apply this framework within the discrete outcome modeling is actually quite straightforward. The derivations of the discrete outcome models imply that the model is compensatory. This is that point I was making, that we only have relative choices. Let me make it really clear. So we have these functions that are going to be utility functions. The question of what is the utility of buying a a van is not a question you could ever answer. I can't measure utility. I can only measure that utility of one thing is greater than the utility of another. But absolute utility, so they're compensatory. People compensate and make trade-offs between things. Okay. So properties of the multinomial logit. So just giving you the background, and when we get to these and estimate these tomorrow, you will find these are really, really fun models, and you can do so much with discrete choice models. So let's work through a little bit of an example and talk about the properties, because there are some pretty important properties that we need to understand about these models. So consider commuter's choice of route from home to work. So we saw actually, we have data that we looked at already that had route choice in there, but we didn't focus on the route choice. Remember, the data we were looking at had, I think it was the first data set where they took a freeway, an urban road, or what was a two-lane highway, and we were focused on the distances and the times. That was the first assignment or lab. So think about that same data set. We have the probability that arterial, probability that a two-lane road, and the probability that freeway were chosen. So there's a choice. I'm about to embark on my way to work. I have a choice between three routes, the same general choice context, and so we can observe the choice, or we can ask people what choice they would make. They're two very different approaches to getting the choice information. In the data set we looked at, we had observed their choices, or what we would call, we have revealed preferences. So another way to think about choices is preferences. People will prefer something over another. The data set that we looked at is a revealed preference data set. And we actually observed choices being made. And then we can set up these functions. So this is that function that I told you about. So the probability that the arterial was chosen is just the exponent raised to the deterministic function of utility for the arterial divided by the sum of all of them. Easy enough. The probability of the two-lane road is the exponent raised to the deterministic portion of utility, which is the x's times the betas for that, divided by all of them, and the same for the freeway. Very simple, straightforward model. These v sub a's are the x betas, okay? And so just like all the other models, we're going to estimate x's, and we're going to estimate the betas from the x's and choose which x's matter in these choice contexts. So there are two types of variables. And there are a number of tricky things about these models, and you have to get. So there's there's actually three, but I'm going to, they're kind of mingled together. So the first one is the variables that vary across outcomes, our alternatives. So tell me a variable that would change across arterial two-lane road freeway. What variable would be type 1 that vary across alternatives? Speed. It's different depending on the volume, traffic volume along the route would be different. Travel time, remember we actually, which is endogenous with speed, we learned. The distance, which is also endogenous with speed. Then remember there's one that has a number of signals? Yeah. So that's also varies as a function of the choice. So there's another type, that's those that do not vary across the alternatives. So what would be an example of that? Vehicle age, the age of the driver. Socioeconomic characteristics, that's right. So they're fundamentally different types. The reason I'm bringing that up to your attention is because the fact that there's two types means that we have to be very careful. And I'll show you when we get there, but we have to be very careful because we can do the wrong thing, try to specify the wrong kinds of utility functions if we don't recognize that we have two different types of variables. And let me demonstrate. So just to cement the idea in your head. So all we do is we look at the differences in utility across alternatives. So if I'm looking at the differences in alternatives across the arterial and the two-lane road, for example, and I have two different utility functions, the person's age cannot be put in every utility function, cannot be entered in every utility function, because it would, the person's age would contribute to some component of utility, but if it's relative, it's only relative, then if I have it in every utility function, then it is the same in all these equations. So if age shows up in the arterial function and all the others, and in this function and all the others, there's no difference. Age is not helping me to understand difference in utility, nor would any of the other sociodemographic characteristics. Only the variables that vary across alternatives could I have in every single utility function. So what we say is that sociodemographics have to be alternative specific. And so we'll see more of that later, but that will throw you up when we go into the tutorial and do some modeling. You might get some error, the LIMDEP throwing you error messages saying, well, we can't solve that. It's likely because you have defined utility functions there, it can't determine the difference because of violating that. Okay. So the differencing estimable parameters relating to the variables that do not vary across alternatives can, at most, be estimated in I-1 of the functions. Okay? So we need to bear that in mind. So the complexity of the functions in these models is enormous. So you think about having just gone through the count models, we have all these permutations, we have zero inflation, we have negative binomial because of variance expansion. Now, in these models, the utility functions can get very, very complicated. So we have to keep track of that and understand that. And so we'll walk through that very carefully in the lab exercise. So given these variotypes, the utility functions are defined like this. So we would have utility functions, and these are the deterministic parts. So there is an error part. We actually don't know all of the components of utility, but we're just looking at the deterministic part of utility, is and we call that V, is a function of these x's for arterial, x's for two-lane road, and x's for freeway. Z is a vector of characteristics specific to commuter n, and Z and x's are the vectors across of the attributes. I have to just respond to this very quickly. Sorry about that. Okay. Okay, so we have the betas that we estimate are vectors of estimable parameters corresponding to outcome-specific variables and x vectors, and these betas are vectors estimable specific parameters according to variables that do not vary across alternatives. So we're going to have a whole bunch of betas, and have a whole bunch of flexibility how we estimate these models. So thinking about tinkering and looking at specification issues in these other models, in discrete choice, they get very complex and potentially complicated quite quickly. Okay, the same thing happens for the constant terms. So we will have at most, and we usually have I minus 1 constant terms. We have to have one equation that does not have a constant term because, again, it's part of that relative utility across outcomes. So we will work through plenty of examples and look at these, and we're going to look at mixed logit models too, which is an expansion of the multinomial logit. And so we'll have plenty of time to have for these models to sink in for us and get used to them. So just like we've done with the other models, we have the parameters. We're going to look at the parameters. These are exactly the same. We have the t statistic, and that we'll look at the t-stats of all our variables. They're exactly the same, which will then have standard errors and p-values, and we will make the same kinds of judgments about the impact of x's. So again, this goes back to an earlier comment. We make this assumption. I'm going to turn that off. Sorry about that. So we made this assumption about using the Gumbel and the differences of Gumbel being logistic distributed, and in the limit, they behave quite rather normally. But excuse me. Technically, they're not as well behaved as other normally distributed. So small samples can be problematic in discrete choice, but we assume that in the limit that we're doing fine, and that these things in the limit will approach t-distribution, or approximately t-distribute, so we can make the same kinds of inference that we do with other models. You've seen that before? So we're going to get the log likelihood values. We can test models, compare models with the log likelihood ratio test. So as I said to you, when I first introduced it, you'll see it in every model. It's super useful. We can compare more complicated models to simpler models and see, are they worth it? It becomes very, very useful for us. Now, if you remember the output we saw in the count models, it comes standard giving you this test for the model with just the intercept term versus the one you estimated. But you can do your own models as well. So you could get the likelihood value at convergence, the log likelihood of say a model with 10 parameters in it, and then run a new model with 8 in it, get the log likelihood and run this test, compare it to a chi-square distribution with, in that case, 2 parameters, and see if you can support evidence for the larger, more complicated models. So we do that outside of the software very easily. Again, you've seen this. We get a rho square, which is 1 minus the likelihood. We've seen that before in the other model. So it's a measure. It's an omnibus test of measure of the goodness of fit of the model. Very useful. And all of this we've seen before, so this is very much kind of review. And it's comforting to know that lots of the things that once we learn about models, that a lot of them are used again. We have a corrected rho square, so that means it's penalized. And here's we subtract the number of parameters, right? So it's penalizing us for making it more complicated. And so we're then able to say, well, just throwing more variables in the model isn't necessarily better. They better give a lot more explanatory power and hopefully make the corrected rho square go up. Okay, so we're actually going to use elasticities in these models rather than marginal effects. Elasticities are, if you remember, we mentioned that they're percent changes. So given a unit, a 1% change in x, what is the percent change in the probability? Okay, and you're going to have probability changes across 4 probability changes, right? So if you change some value of x, it's going to change the probability of being the first outcome, the second outcome, the third outcome, and the fourth outcome. So it will have several impacts on the outcome model. So they're very different in concept to what we've been looking at. These are all probability-based and look quite different. So, and again, like in the account models, the elasticities are dependent upon, they're in a nonlinear model. So they're usually averaged over all of the x's, and they're the average elasticity. Okay? Because elasticity will change depending on the values of x. And so we'll do an average. Usually it's the sample average. But you could compute specific elasticities if you wanted to, and these are the formulas for doing that. So it's interpreted as the percent effect that a 1% change in x has on the outcome probability. So econometricians tend to use this concept. And it's a very useful one. That is, if elasticity is greater than 1%, then we say something is elastic. And if it's less than 1%, we call it inelastic. Okay? So for a 1% increase in x, if we see a 5% increase in y, we say that's a very elastic behavior. Okay? And that is another way of saying it's very influential versus not that influential. Okay, the values are point. This is what the point I just made. The values are point elasticities and are valid only in small changes of x. Okay, and the considerable error may be introduced when elasticity is used to estimate the probability change caused by doubling of x, for example. So you're going in a very different range of x, and you would have to compute it specifically. They're not applicable to indicator variables. So there's some new elasticity or pseudo-elasticity that needs to be calculated for an indicator variable. Now, I'm pretty sure that Bill Green says that LIMDEP does that automatically. And this is done automatically for you. We also have cross-elasticities, and we'll look at these in our tutorial. So a cross-elasticity may be interested to determine the effect of a variable influencing the probability of outcome on other the probability of outcome I. So we'll talk about that in the modeling and talk about it here as well. Yeah?
Yes, I think in the previous slide,
yeah.
the expression is that pseudo-elasticity.
The cross, which one? This one?
Yeah. Yeah.
This one?
Yeah, this one, the one on the top.
Yeah.
This is the pseudo-elasticity?
No, that's that's the pseudo-elasticity. Nah. Yeah, that's the pseudo one. But we don't need to do these by hand. We do these. Yeah, that other one's the simpler one. That's the elasticity.
Oh, because elasticities are not applicable to the indicator variable. That's
Right.
why, right?
Right.
Yeah. So it is more like the marginal effects.
Yeah, it is more like a marginal effect. Okay, so the cross elasticities are very interesting because, we'll see there's a limitation on the cross elasticities of the multinomial logit that we can get around with other models. So this is the formula for the cross elasticity, and what you can see here is that the cross elasticity implies that there's one cross elasticity for all I not equal to j. Okay? So that's interesting because that means, and the implication of this is it means that for an increase in distance, for example, on the arterial results in an equal increase in the likelihood that the two lane and free will alternatives will be chosen. Now, and that's an artifact of this model specification. It's an artifact of this model specification that cross-elasticities are equal for the other alternatives in the model. It may not be realistic. And we'll do an example in class to show this and show why when we'll work it out and we'll show you the cross-elasticities and we'll see that, wow, that may not be a realistic assumption. If we increase distance, why would there be an equal increase in the likelihood of the other two alternatives? Maybe increasing the distance for an individual would make them more likely to take the freeway or the two-lane road. But the artifact of the model is that it provides equal probability across the two alternatives. And that is one artifact of the limitation of this model, which we will talk about. It's an artifact of the independence of irrelevant alternatives assumption of this model. Okay, so the other thing we can do with these models is, because they're compensatory, that is, we're trading off the value of this versus the value of that, the marginal rates of substitution are computed to determine the relative magnitude of any two parameters estimated in the model. So a marginal rate of substitution is essentially how much would you be willing to trade off this attribute for this attribute. And it's a very, very useful statistic that comes out of these models. So this rate is computed simply as a ratio of parameters for any two variables. So marginal rate of substitution for B versus A is just the ratio of those two parameters. So it's very easy to do. And we'll do an example of that in class. Am I done? Oh, I am. That's the end of that lecture. Okay? Okay, so I'll say one more comment about the previous slide. So what we're going to talk about a little bit in the next lecture before we then jump into the tutorial for this is that one of the assumptions I didn't talk about much, but we will in the next lecture, is that the way this model is based on this assumption of independence of irrelevant alternatives, which stems out of identically distributed error terms. And there are a couple of limitations that arise from that assumption. And we used to make a huge deal of it. We used to make when I took this course, a similar course, when I was going through my PhD studies, this was a huge, huge deal because we didn't have the computational ability to get around this problem very easily. And so we spent a lot of time talking about it. I'll spend relatively less time talking about it than I heard when I was taking this class. There are some really easy now workarounds from this assumption. And so we at the time I took this class, they didn't have a mixed logit model that people were using and computationally easy to do. But now we do. And we also have what we call nested logit models, which are a way to get around this. But it's so easy to do a mixed logit. I think with that I'm going to end with talking to you a little bit and start to get you to think about random parameters, because that's what a mixed logit is. So who has heard about a random parameters model? Okay, very few of you. So this is a pretty cool concept, but it's a little you remember I said things get more complicated and we're trying to develop models that get more and more complicated. And this is one of those little things that gets more and more complicated. And so I want to walk you through conceptually what a random parameter is, because we're going to be starting to get into these and what it means. So I'm going to tell you about it with an example. And we can estimate random parameters models with just any of the models that we've done so far. But the mixed logit is a random parameters multinomial logit. And it gets around this problem of the cross-elasticities and the independence of relevant alternatives. But let me just talk about random parameters in general. Okay. Our models we've looked at so far have all fall into the class of what we call fixed effects models. Inherent in everything we've done so far is the assumption that when we estimate a beta, that it applies for everything or everyone in the population. So what was the model we estimated earlier today? We were looking at count models. What was one of the variables we had in there? We had state root 520, right? That was one of the variables. So let's say we had one of those models, and we have a parameter estimated for state root 520. One number, one beta. The assumption is that that beta applies to everyone. So in that model, it means that the interpretation of that beta is that that beta has this equivalent effect on the days per week of early departures for everyone in the population. And we have to believe that, that's the truth, right? We have to, when we estimate that model, we're saying that's how people behave. Everyone responds to the state root 520 the same way. But if you came along and said, well, wait a minute, what if every single person behaved differently with respect to the 520? That is, the 520 has a different effect on the number of days that you would take and depart early. And so I want to give every single person, if you were all the people in that study, I would give each one of you a beta. Instead of just assuming you all follow the same beta. That is what we would call a random coefficients model. And why do I say random? It kind of seems strange to say random. Well, the way we deal with that is we say, well, okay, I'm not really going to estimate a beta for each one of you individually. I'm not going to identify the beta for each of you. What I'm going to do is say that all of you collectively share a beta that might have a mean equal to close to the one that we estimated for the fixed parameter, but that you have a spread around that mean. And then I will say that parameter has a distribution, maybe a normal distribution with a mean close to the fixed effect parameter and some variance, and that all of you collectively would have parameters that fit that distribution. But in terms of interpretation, it allows us to say behaviorally that you all are different from each other in your response or the effect of 520 on your departure times. So, intuition, let me see if your intuition's kicked in gear. So when we look at the fixed effect, the beta, what is the test we're looking at? What is the test we want to do for beta? Whether it's 0 or not. Okay, right? We got that down. So if I'm doing a random parameter, this is a tricky question. If I'm estimating a random parameter, what test do you think I would want to do, or I could conceive of, that would tell me whether a random parameter was true or not? That there was evidence that we all behaved differently. What's that?
Does not follow the mean of the distribution.
Okay. Yeah, there's a few of you coming up. So I did hear the right answer, and there's no real wrong answer, but the right answer in terms of what we do. Think of it in terms of if the standard error of that mean was 0, or we couldn't rule out 0 as being the value of the standard error of that distribution, then what we could say is that that's a fixed effect. A fixed effect is saying, I'm assuming everyone has the same thing. And if it's not true, then there would be sufficient variation in that parameter as reflected by a standard error. If the standard error, the confidence of the standard error of the confidence interval included 0, and the standard error of the parameter was 0, that means it's a fixed effect. So that's what we do. So random parameters models, we test the significance of the standard deviation and would then be able to test, do you all behave differently with respect to the effect of state route 520 on departure times? I can test that. And if I can reject 0 as a value of the standard deviation, I can then say, I'm going to build a model that allows you each to have your own parameter for that. Okay? And we can do that with any kind of model. And it is sufficiently more complicated, right? It's sufficiently more complicated. Not that much more complicated, but it's more complicated in estimation, drastically more complicated in estimation. But we've only added one more parameter. So in a fixed effect, we've got a beta, and it's the mean beta. In a random parameter, we have the mean beta and its standard deviation. We've only added one parameter, so it's not that much more complicated, but estimating it is more, and I'll talk to you about that later. So that's the concept of a random parameter model. It's not actually, or a random coefficient model. It's not that hard, actually, conceptually. It's quite straightforward. And again, this is all about what is the real complexity in the data that we could justify. So anyone can think of like in utility, some obvious things that might be random parameter that we could think about in utility functions. Let's say we're talking about what vehicle you purchase or what mode of transport you purchase, whether it's a scooter or a bicycle or a car. What factor do you think could be random parameter? Any ideas popped ahead? What's that? There are a lot of possibilities, but one that's usually pretty common is price. Because if you think about it, if we assume a fixed effect for price in utility functions that says we all respond to price the same way, and well, response to price actually often depends on income, and so people with higher income are less sensitive to price. We know that. Economists have known that for a long time. People that are lower incomes are more sensitive to price. So, so that's one. If you have just price as a variable in there, often can be a random parameter. But interestingly, we can have models that have multiple random coefficients in them. And we can test whether they're random coefficients. And you think about it, then all of a sudden your predictive function now is a function of all of these sorts of things. So I'll leave you with a little story about this, and we'll finish today. So I was taking a course when I was actually at Georgia Tech as an assistant professor, and I used to take a stats course. It was a favorite thing to do. I'd take a stats course every summer break, and I went down to take a survival model course, which we're going to talk about in this class. And I was the only transport student in the class, and they were all mostly medical students in the class, and we were talking about survival models. And I know we haven't talked about survival models yet, but the principles are the same. And so we were talking about survival probabilities, and one of the variables was doctor. Okay? So they had done the study, and the study was they were looking at how much time would elapse before, after surgery, before an infection would occur. So it was the measurement was days. So you have your surgery. We had a bunch of people in the study that had surgery, and they say, okay, you're in the hospital bed. You just had surgery. Now we're going to count the days and see if you have an infection and how many days elapse before you have an infection. Some people would never have an infection, right? But others that did have an infection, that's censoring, right? And then some would have an infection 10 days in or 20 days in, whatever. And one of the variables was doctor. And And they had entered doctor type, and there were about 6 or 7 doctors, A, B, C, D, E, and F, and G or something. And they had doctor entered as a random effect, a random parameter, right? And so you were trying to predict survival, and we had one of the variables was doctor as a random effect. So we just had doctor in there, and which means that they have an average effect on the survival probability. Some make the survival shorter, some make the survival longer. But the way we estimate that model, we don't know which doctor is which. And as a transport guy, I raised my hand and I said, why don't we estimate those doctors as fixed effects? Dr. A, Dr. B, Dr. C, I said, if I was a patient, I would very much want to know the fixed effects for those doctors. Because I would look, then you'd be able to look up and say, Dr. C is the worst doctor. Your survival probability is the shortest with Dr. C, and the longest with Dr. F. He has the longest survival probability that you will go a long time without infection with Dr. F. And the response was, oh, Simon, the doctors funded the study. They would never go for a fixed effect estimation, so we have to make it random that we don't know how doctors are performing. So, but you think about it, that those are the kinds of questions we ask when we're estimating models and looking at what's really happening underneath and how we model the process that's happening. So, so now we've, just in 2 short days, we're talking about the most complicated model that at least we do in transport generally, and with a random parameter specification, which is about as complicated as it gets. So we're already into the deep waters, and then tomorrow we'll get into the estimation of this, and then and do one more lecture, and then we'll do some estimation. We'll spend quite a bit of time working with these models because they take a little while, and they're fun and they're interesting. And I can say that if you get a chance to do some discrete choice modeling in your work, it's really, really rewarding and really, really interesting work, because you can examine a bunch of really interesting choice contexts and in transport, and why people. So somebody mentioned, I don't remember who it was, that they were studying residential location choice. Really, really interesting work. Why do people choose to live in certain locations? And so we can study why people do. Well, at least we try to understand why people make the choices they make, and that's really, really a powerful tool to examine that and identify what factors influence people's choices. It's really, really, really rewarding. So, anyway, that's all I have. And any questions before we wrap up for today? Really good question. Really good question. So, okay. We can get a little bit deeper into this tomorrow, but I'll give you a little flavor of this. If you remember, we mentioned there's 2 types, and I didn't remember the second time. I said there's revealed preferences. When we observe people making choices, the data set we have are revealed preferences. We saw people choose a route. We could also set up what we call stated preferences, where we ask people, if you were given these choices, which route would you choose? If the time on this one and the time on that one. So it's more of a hypothetical choice. And we have, the literature is full of both types, revealed preferences and stated preferences. The interesting part, coming to your question, is that the argument has always been, well, revealed preferences are better because there are people making actual choices. And when we observe people making actual choices, then we think the utility functions are well set. They consider them very carefully. They know they have actual costs, they have actual ramifications of those choices, and they make decisions. Whereas in stated preferences, people say, well, they didn't really spend money out of their pocket. They didn't really buy something, so can we rely on those choices? The interesting part is, in revealed preferences, often people don't know the attributes of the non-chosen alternatives. So if we have a set of, let's say, mode choice, and I'm talking about rail and bus and car and cycle or something, if you ask people who make real choices every day, what is the travel time by bus that you didn't choose from your location to work? So I don't know, I've never taken it. I don't know actually what the travel time to work by bus is. It's an hour. Well, the reality is, and there's literature to show this, that it's actually usually a lot less than what people think it is, or a lot more. But they're never usually very accurate. And so your point is that even though we have revealed preferences sometimes, we don't think that people actually know the attribute values. The x's that we think are important, the people making the choices actually don't know the x's. And so oftentimes we have to come in as researchers and fill those in and say, well, if you live there, your bus travel time to work is 45 minutes. The problem is, though, that person, that real decision maker, doesn't know that. And we think they're using that information in their choice, in their utility function, when they think it's an hour, or they might think it's 30 minutes. So it's a real problem, and it's the argument to say that actually revealed preferences aren't as great as we think they are. Stated preferences, at least when I ask you to make a stated preference, I say that route is 45 minutes. And now make your choice knowing that it would take you 45 minutes by bus. So it's a long answer to your question, but it's a really interesting question in the revealed stated preference domain and looking at choices because in a lot of choice contexts, people don't know the attributes of the non-chosen alternatives. And I think one of the most complicated papers I've ever done was on that subject. It was a horrendous paper. I don't ever want to look at it again. But it was on that exact thing. And so, actually, I'll tell you a little bit about it. So what we did is try to impute all of those. We haven't talked about imputation. Imputation is filling in data on the best of information that you have on the choices that are not chosen, because we believe people don't know what those are. So how do we impute that? And impute those attributes and then build a choice model on that. But it's a problem, and it's a difficult one. So there's not a really easy answer for that, but you raise a significant issue. Are they revealed preference data? Yeah.
So
Yeah.
you also did the imputation on revealed preference data?
Yes. I did that a few years, maybe 4 or 5 years back. But like I said, it's a horrendous modeling effort and complicated thing that I don't care to ever repeat.
Yeah, because for imputation, we need to know what could be the most possible choice.
Yeah. There's so many wonderful topics to discuss, and imputation is one of those. And if you have missing observations, how do we deal with that? And how do we deal with that sensibly? And there's a lot of really interesting topics there. But very, very briefly, if you have missing data, but you want to use it to estimate something, then the idea, well, if you fill it in, and with a single value, you've actually pretended to have a level of certainty that you don't have. And so the argument would be that you would fill it in a Markov chain Monte Carlo approach, where you fill it in with a distribution of values and do it repeatedly to estimate the variance of the uncertainty associated with the missingness of that. And so you estimate the uncertainty caused by not knowing that information precisely. So, but very interesting stuff. So in fact, I would have to say, the book that we use, we've just signed a contract 2 weeks ago to do the 3rd edition, and one of the chapters that I will be writing will be multiple imputation, how to deal with missing data problems and how to fill those in, and do it scientifically so that you can rely on that. But yeah, tough problem. Anyway, any other questions? You dare ask me any questions now? That was like a 15-minute answer, so I was like,
No, I think we can all go through the presentation, and tomorrow, first thing in the morning, we will start the exercise. Because it will also be continuation of multi-level and logic. So if we have a question, we can discuss it. Okay? So again, then tomorrow 9 o'clock you come here, and tomorrow again is going to be a long day, like today. So yeah, be prepared. I would suggest that you bring your laptop anyway tomorrow here. If we need to use it, we will use it. Otherwise, please carry it.
well, because we won't have a super long, we would have at the most an hour lecture, and then we'll go straight into the modeling.
Yeah.
So tomorrow's modeling session will be more modeling than lecture in the first part of the day tomorrow. So these models are really cool, I promise you. They're really, really fun. So. Okay. No. So I've got all the flight information now. So these are new flight details.
Okay.
Terminal.
So arrival is then 1935.
Yeah, 7:35. Yeah.
7:35 and terminal
3
and then is terminal 3.
You said.
Oh yeah, terminal 3 is basically. Yeah,
You said
this
you were telling me 3A. Yes.
that is gate 3.
Gate 3.
Yeah, but it's okay. Yeah, if I
Tell me
have
gate 3. Yeah, whatever.
Yeah, if I can then just send it to the driver.
Yes. And if you can give the I'll text your driver